life's been kind of crazy for me lately. As you can imagine, with the simultaneous release of my last stats video and my first hip-hop single, life's been kind of crazy. Obviously, over the past few days, I've seen an increase in the number of fans that I have. It's really validating to see that fan base grow, and I want to make sure that I don't forget where I came from. And so I thought it would be nice if I brought in my biggest fan to help me with this video. So here they are, my biggest fan. Right? Biggest fan I have. I have lots of fans. This is the biggest one I got. They don't say much, but I feel like the connection is electric. And so, yeah, they're going to be hanging out here with me today to do this video for you. Previously, we've talked about probability distribution functions for general random variables. So once we define a random variable on an experiment, right, we can distribute probabilities among the outcomes of that random variable however we want. And as long as it satisfies the two conditions to where each probability is between 0 and 1, and that the sum of all the probabilities add up to 1, this is a probability distribution function. We want to now start talking about specific experiments or specific types of experiments that come up enough that special study has been devoted to them, and they have their own name. And the first one we want to talk about is called the binomial distribution. The binomial distribution comes about whenever we look at binomial experiments. Now, for an experiment to be classified as a binomial experiment, three things have to happen. The first is that we have a fixed number of trials. And we're going to call that n. So for whatever experiment we're talking about, if it's going to be a binomial, we have to have something that we're going to repeat. And we have to repeat that the same number of times regardless. Now, we're kind of familiar with that already. We've been doing lots of examples about flipping a fair coin twice, or flipping a fair coin 3 times, or drawing a marble out of a jar a certain number of times. These are examples of experiments that have a fixed number of trials. So, let's say we have a fixed number of trials. What's the second condition that has to be true for us to have a binomial experiment? The second condition is there has to be 2 outcomes, and only 2 outcomes. And of those 2 outcomes, we're going to label one as a success and one as a failure. And we let P be the probability of a success. And then we can define Q to be equal to 1 minus P, and that's going to be the probability of a failure. Now, a couple of things here. The first is that we already said that we're going to do a fixed number of trials, so this is going to be repeated. So in order for this to be a binomial experiment, this probability of success has to be the same throughout all of the trials. So if we're going to do 10 trials, let's say, of someone shooting a free throw, we would need a situation where each free throw had the same probability of going in, right? We wouldn't want a situation where, like, a player starts warming up and the probability of hitting the first 5 are significantly lower than the probability of hitting the second 5 after they've started shooting and getting warmed up. So we have a fixed number of trials, and each of those trials has only 2 outcomes that we're going to label success and failure. Now, the other thing about these 2 outcomes is which outcome we label a success is completely arbitrary. It depends on what we're interested in studying. It does not have to be the good outcome, right? If we want to talk about the likelihood of a certain number of people dropping a class, then we can talk about a success being a student drops the class. Even though as an instructor, an educator, I would not consider that a success. The point is, for a binomial experiment, a success just means the outcome that we're interested in, and the outcome that we're interested in counting, and a failure is the other outcome. And then the last condition that has to be true for this to be a binomial experiment is that these trials must be independent. And we've talked about independence in the past, but the idea here is that if we're going to repeat this trial over and over and over again, we want to make sure that whatever happened on the first trial doesn't impact the outcome on the second trial. And what happens on the second trial doesn't impact the outcome on the third trial, and so on and so forth. If we have these three conditions on our experiment, then this is what's known as a binomial experiment. And each of the trials in a binomial experiment is called a Bernoulli trial. So if you hear the word Bernoulli trial, that just means a single trial out of a binomial experiment. So now, let's talk about what we know if we know that an experiment is a binomial. All right, so let's consider a situation where we've defined a random variable x, and for whatever it is, we've determined that it meets the three conditions for being a binomial experiment. And so that means that we have a fixed number of trials in, we have two outcomes, one we've labeled a success and one a failure, and the probability of having a success is p, and those trials are all independent. So that makes this random variable x to be the random variable associated with a binomial experiment. And so a little bit of notation is we would say x is, and we use the tilde or the squiggle or whatever you want to call it, and we use a capital B to represent binomial. And there's lots of different binomials, right? Because a binomial can have some fixed number of trials, but that number could be 10 trials, 100 trials, 1,000,000 trials. So we specify that it has n trials. And then the other thing that tells us exactly what kind of binomial this is the probability of success. And so we also put the probability of success p. So for example, if we had an experiment that is going to do 10 different trials and the probability of success is 0.35, and so say that random variable is a y, we would say that y is a binomial with 10 trials and a probability of success of 0.35. So that's the notation that we're going to use. So now back to our random variable x, which we know is a binomial, and it has n trials with a probability of success p. Now, the two things we've talked about recently about random variables is calculating the expected value of a random variable and the standard deviation of a random variable. And those can get complicated. There can be some computation involved, especially if we have a lot of trials. That's potentially a lot of work. But because the binomial shows up so much, some mathematicians have put in the effort to come up with a formula for these. So for any binomial with n trials and probability of success p, the expected value of that random variable is going to be equal to n times p. And that's because the random variable here, this x, is the count of the number of successes that we observed out of n trials. Right? The thing that we're counting with a binomial experiment is we have n trials and we want to know how many of them ended up in a success. And so if we ask ourselves what will we expect the expected value to be, right? Let's consider a situation where we had our example binomial over here, and let's say instead of 10 trials, right? Say this was 100 trials, and we had a probability of success of 35%. So if you did something 100 times, and each one of those has a probability of succeeding 35% of the time, how many of those would you expect to be successes? Well, the obvious answer, and the answer that turns out to be true, is that we would expect 35 or 35% of those trials to be successes. So we would expect that the random variable y, the expected value of that would be 100 times 0.35 or 35. So this n times p makes some sense, right? If each trial has the same probability of success, we would expect that proportion of the trials to be successes. Now, the expected value formula isn't much more complicated, or the standard deviation formula isn't that much more complicated, but standard deviation in itself is a little harder to visualize. So we're just going to have to go with this one. And so then the standard deviation of x is just going to be equal to the square root of n times p times q. And in this case, remember that q is just the probability of failure. So another way that you might see this written is n times p times 1 minus p, and then the square root. So using these two formulas, we can get an idea of the behavior of a binomial experiment. And so what we're going to work on now in class is identifying when something is a binomial, when it's not. And if it is a binomial, how to calculate its expected value and standard deviation. And then how to use some materials that we're going to have available for calculating other probabilities associated with a binomial experiment.